Thank you, Alexei. So, hello everyone. So, my name is Sergey Kholkin. I am a PhD student of Alexander Kholkin, and I will be helping him to deliver this mini course for this beautiful summer school. And so, as Alexander said, he would have 2 lectures on flow matching and beach matching tomorrow, and they will be followed by my seminars. First, of course, on flow matching, and the second one on beach matching, complementary for the lectures. So, what we will go through today? Our today's plan is to recap on practice what Alexander told us about flow matching models. So we will build several flow matching models for 2 types of data. For two-dimensional, to better visualize the different properties of flow matching models, and the image example to test the scalability of flow matching model. So first, of course, we start from two-dimensional data, and we will train several flow matching models. So as Alexander told us in the later part of the lecture, that you can get different flow matching models with different transport coupling plans. And with different sequences of distributions that we build. They yield different flow matching models. And we will try to build 4 different probability sequences for different couplings and see wherever they produce better or worse flow matching models. So, I know, do you have a Google, you can try it by yourself. If you have a notebook posted somewhere with me. So the only thing that you need is basically NVIDIA GPU to run this notebook. So, great. Let's start. So, of course, we start from some imports, and there are, I believe, nothing too interesting except for the TorchGene library. And of course, like everything here is based on Torch. So TorchGene library is a library that is dedicated to the ordinary differential equations in the Torch ecosystem. So why do we need it? So flow matching models are based on ordinary differential equations, and we need simulations of simulation algorithms for ordinary differential equations to actually perform the data generation process. So that's why we do need this TorchGene library. This is actually a very good library. Try it sometime. And yeah, of course, we run on NVIDIA GPUs here. So here we have some visualization utils, seeding as usual, right? Yeah. And so here we define the data. So this is the, let's process. The first two-dimensional data that we will be working on. So we'll be solving the problem of unconditional generation from a Gaussian distribution to the 8 Gaussian distributions. We will wait a sec. So as Alexander said, we can actually we do have 2 distributions, right? So the first one, which is P0, starting distribution, and the ending distribution, which is P1, right? So basically, in general, we can have those 2 distributions arbitrary. For example, as Alexander said, a transport from 8 Gaussians to 8 Gaussians. But here, our source distribution that we'll start with will be just a Gaussian. So this will be just a generic generation problem. So yeah, as you can see here, we will start from this blue points and go to the orange points via our flow matching model. Right? So then let's go recap some theory that will help us in our implementation. So first of all, yeah, so what do we have to define to train the flow matching model is the sequence of these distributions, Alexander told, right? So we have this arbitrary distribution P0, which is the start of our generative model, and distribution P1, which is the end of our generation model. And our general task is to start from points from distribution P0 and end points from distribution P1. Very simple. And again, there are these intermediate distributions, which there are many ways to construct those distributions, and we will try 4 of such ways. So again, a bit of a recap. So what is the main thing that we have to actually train in our flow matching model is the vector field. The vector field with some data point xt as an input and with some time point also as an input. The output would be also a vector field for our ordinary differential equations. And then starting from some data point x0, we can inference our ordinary differential equation by some arbitrary simulator of ordinary differential equations. That's why we do need this torch-gene library, which can be your favorite solver, for example, Euler solver, Dopre solver, Runge-Kutta solver, whatever you want. Yeah. So here our task is to train the vector field, to find such a vector field that will allow us to perform such ordinary differential equations based transport. So how do we train this? How do we train this vector field? How do we define it? So except for the distributions P0 and P1, we have to also define interpolation between them. And here, in our case, we choose the simplest one, which is just this linear interpolation, right? So yeah, it's very simple, just linear interpolation between data points x0 and x1, where x0 is sampled from distribution P0, and yeah. There is no axis. Okay, I hope it will be resolved. Yeah, so then x0 is sample from P0, x1 is sample from P1. And then, again, very simple regression problem that we solve. So we just take the samples x0 and x1. We just compute the xt, which is just the result of linear interpolation between x0 and x1. And regress it upon the difference of x0 and x1. So this is like very, very simple algorithm, just plain regression. Yeah, that's one of the ways to get the corresponding vector field that transforms distribution P0 into P1. However, what is noticeable here is the way that we choose the pairs for our algorithm, pairs of x0 and x1. And as Alexander told in the later part of the lecture, there can be a lot of possible pairings between x0 and x1. They are called transport plans. And you can see that they are there in the expectation when we take this x0 and x1 from distribution P. Different distributions P induce different optimization problems and different minimums to this optimization problem, which in turn yields to different vector fields. And each of these vector fields have their own properties. Yeah, and what do we do in practice? We just parameterize this vector field V by a neural network V theta and just solve this regression problem with empirical samples x0 and x1. That's it. Again, flow matching is very, very simple algorithm. So yeah. Okay. Then we will go straight to the implementation in particular for our two-dimensional case. And first we start from a neural network, right? So as I've told previously, our neural network has a xt point, which is data point as an input, and also time point as an input. So that's why usual choices for such neural networks are, for example, multi-layer perceptrons with time conditioning, or unique neural networks for images with time conditioning, or diffusion transformers with time conditioning. Here we will use a very, very simple plain version, the MLP, that consists of several residual blocks in such a form on top of each other, and v time would be just another input. Yeah, you see. So we have this input dim, which is the dimensionality of our data, and 1, which is the dimensionality of t. Of course, if you want something more expressive, then you most likely would need to implement some time conditioning via some positional coding. But yeah, that will be also applied later. Right. So again, our neural network is just this stack of residual blocks here, residual MLP blocks here. Then we define our flow matching model class, which takes the data dimensionality as input, the width of a neural network as an input, and number of residual blocks, of course. Then we have our forward function, which is just the forward function for the vector field of our flow matching model. And then the interesting part. To train, again, our flow matching model, what do we have to define? We have to define the target, which is this UT, which we regress on this part, and the way to get sample 60. So let's implement both of these parts. Again, they are rather simple, but tomorrow they will be actually more complex, but now they're quite simple. So again, here in this function, we just have to compute the xt, and xt is just the linear interpolation between x0 and x1, and in our particular case here, x and y. So what do we do here? We say that y is x1 sample, right? And we just multiply it by the time. So that when the time is equal to 1, we will get just y sample. And then we just multiply the x sample by 1 minus c. Very simple. And here we have our xt sample that we will use as an input to our neural network during training. Then, as a second part, what we have to implement for our flow matching model is the target, is the regression target. And to recap, the regression target is just the difference between x1 sample and x0 sample. So let us just implement it. It is very simple. We just take y, difference between y and x, and that's it. So for training, actually that is like all that you need for training. Then there is this a little bit more complex part, which is mostly related to the inference, because again, during inference stage, we have ordinary differential equation model, and we have to simulate ordinary differential equation starting from points x to the point y. Again, we just use the Torch-Dean neural ODE solver for this particular purpose. In our particular case, it would be a Rectified solver, which is actually a very good solver and is used for flow matching models, I think, in most cases, with some time grid specificity. So in ordinary differential equation solvers, you can define the either sparsity or the density of your solver in terms of time points t where you evaluate your function, right? So the less the difference between nearby points t, the more accuracy is there to your ODE solver, right? But the more time points you have, the more function evaluations you have, because you would have to evaluate your vector field at each particular time point. And that is time consuming. And that is actually one of the most reasons why flow matching model is quite time consuming on the inference, is the fact that you have to perform this simulation where you have to do a lot of evaluations of your neural network. And here we aim to the 100 evaluations of our neural network, or I think maybe more in this Rectified solver version. And you can, of course, extend it, for example, to 1000 if you want more accuracy to your ODE solver. Or you can even lower it to, for example, 10 if you want speed and lower accuracy. So there is some trade-offs to be here. All right, so Yeah, you can also use different ODE solver, whichever you like. Even Euler solver will actually do fine in most cases, I think. Yeah. So here's some utility to generate trajectories, but this is basically the most important part here is just the definition of xt sample points from our trajectories, the target for our regression, and the way to sample from our flow magic model. Then we just go straight to training, and the only, I believe, part that we have to define here additionally for the training is the pairing between data. So again, we can have many ways to pair our data samples from x0, from distribution p0 and distribution p1. So we start from the simplest one. That is, I think, most common in flow metric models, which is independent one. When you sample samples from one distribution, from our distribution, you pair them randomly and just draw a linear interpolation between them. So in terms of implementation, it is very simple because you just sample from two independent distributions and then just do nothing for them to induce some correlation between samples. Yeah, let us so run some functions. Yeah, and so here's the visualization. So what do we do here? So we have this source distribution, which is green, and we have the 8 Gaussian distributions. That is our target. And what do? We pick random pairs of random green points, random red points, and we just draw a linear interpolation between them. So obviously, since there are no correlation between these points, then we will have a nightmare of different linear interpolations that are intersecting and are basically all over the place. And it doesn't actually seem very nice, but it produces quite decent flow magic models, and it is a good starting point as well. So with these pairings, we can already train a flow magic model with what we have implemented by now and see what kind of quality will we receive. Yeah, so let us launch the training. I know how much will it take. Yeah. It seems like no GPU today. But yeah, okay, I have all the inputs. So here's the training function, and again, this is the training procedure is just the training procedure for the L2 regression, which is very simple. We just have our flow matching class, which is basically our neural network, and sampling function, which is the way to get paired samples that we have here on this plot. Then we have, of course, like learning rate, number of epochs, batch size, all these standard parameters. Define just the optimizer, go through the epochs, and solve very simple L2 regression. Where the loss is just, it's just mean squared error. There is like nothing interesting here. And it's very, very simple. It's very good. So if we will run all this training, which takes like 1 minute on A100 GPU, we will receive this result. So what is this in particular? So on the left, you can see there are trajectories of our final flow matching model and the overall samples from our model. So you see that we have here these red distributions, right? These red points, they are already samples from our model. And so if you will recap the target distribution that we had in mind with these 8 Gaussians, samples from our model actually follow this pattern very well. There are clean 8 Gaussian distributions, and they are all round and not triangular, so everything is in place. But, however, if we will take a look at the trajectories, you can notice that they are not exactly straight. Well, yes, they are, let's say, relatively straight. However, if we will take a look at, for instance, yeah, can you see? Yeah, you can see. This a little bit curvy trajectories. And here trajectories are also curvy with like one or two curves. Yeah, curvy trajectories are harder to simulate. You would need more accuracy of your ODE solver to actually simulate these trajectories. While they are relatively nice, we can do better. We can do better. And also you can see the loss here, which you can see actually is quite noisy. But it just maybe because it converges quite fast. Yeah, and you can see that like it converges up to some lower bound, like in, I don't know, 100 gradient steps. So model is trained very, very fast. And yeah, well, this already is quite good because yes, we sample from our distribution quite well and we have relatively same trajectories, but can we do better? Can we do better? That's the question. Here comes the optimal transport mini-batch plans and the general coupling theory. So again, for different transport couplings that you have at the start of your model, you receive different flow matching models. And some of them have straight trajectories, some of them do not have straight trajectories. And optimal transport mini-batch plan is one of the ways to enforce straight trajectories with relatively cheap cost. Yeah, by the way, up to this point, do you have maybe some questions regarding implementation or anything? Okay. Okay. Yeah. So we will go with optimal transport mini batch plan. So what this optimal transport mini batch plan does. So again, we sample some points, some mini batch from distribution P0. We sample some mini batch from distribution P1. This one. And then we have to construct the pairs in some way. And we utilize the optimal transport theory to construct these pairs. So what we do is we take these two mini batches and we try to find such a pairing between those particular empirical samples that induce less difference between those samples. So we minimize, in a sense, L2 distance between X and Y's in our pairings in this particular two mini batches setup, which is actually very much known problem with a lot of solvers, also known as optimal transport solvers that solve this problem. And yeah, from this POT Python optimal transport library, that is actually very nice for solving optimal transport on empirical samples. And yeah, so here's some code how to do this. You can take a look later. They're actually like nothing very complicated, but still. And yeah. So the question: how does it look like? How does it look like? And it looks like this. So here's actually a huge contrast with respect to the previous coupling that we had. I will recap a little bit. Yeah, this one. So you can see that there are trajectories all over our plane. We have intersecting trajectories, and yeah, it seems like a spider's net. However, this one, trajectories almost do not intersect. Yeah, trajectories almost do not intersect, and they are very short actually, because like what our optimal transport mini batch plan does is tries to shorten these trajectories. And we can see exactly that. And in general, it seems a lot nicer than the previous one. And we will see that it actually also induces the stated trajectories of our engine model. So again, here we define some of the hyperparameters. We use exactly the same training procedure as for the previous one. And yeah. And another beautiful thing about flow matching is that there are not a lot of hyperparameters. There are not a lot of things to mess up. Like because all the hyperparameters are very, very basic. And the only thing that you can mess up is maybe learning rate, but I don't think so. So it's on practice, it's very, very nice algorithm. Yeah, again, we can train. And another thing is that since we have to solve an additional optimization problem to construct mini-batch optimal transport couplings on each of the gradient steps for our model, then each of the gradient step takes more time. Because, yeah, again, let's take a look at our training function. First, we sample data pairs, and then we do construct the target and solve the regression problem. And now this sampling function that constructs the pairs from distribution P0 and P1 solves an additional optimization problem, which takes some time. And so, for instance, the first one, which is with independent transport coupling, when we do not solve any optimization problem during training additional one, then we can see that it takes 32 seconds on GPU A100. And if we will take a look at the solution with the mini-batch optimal transport coupling, where is it? It takes like, yeah, 1.5 minutes. So we have lengthened our training for 1.5 minutes in 3 times. Yeah, but at the end, we actually get stated trajectories. So you can see that, so this is the result of flow matching model training with mini-batch optimal transport coupling. And while trajectories are actually not yet straight, not yet fully straight, right? However, these ones are almost fully straight. There are like this trajectory, which is curvy, but yeah, and this trajectory, which is curvy, but overall, most of the trajectories are almost fully straight. So we have done significantly better than with independent transport plan, where like each of the trajectories, I believe, had at least one curve. And this is better because, again, with stated trajectories, there are less load that we put on the accuracy of the ODE simulation solver. And yeah, that allows us to induce less error in the end. And yeah, also you can see that we still generate the distribution very well. We have all the 8 Gaussians, and they are all round and very nice. Yeah. Again, some questions? Yeah. А вот это нет?
It fails to run trainer with independent plane. When I try to run train FM function for flow matching with independent plane, it fails, and it says that xt equals torch.cat something, expected tensor as element 0 in argument 0, but got non-type.
You have to implement it yourself. It is there's you have to implement the sampling of XT, the linear interpolation yourself, the target for the regression yourself, which is compute UT function, and the maybe loss function, but I don't remember.
So this is exercise. It is
Yeah, this is kind of exercise. I already done it right here, but yeah, you also need to launch a notebook. You should do it yourself, and it's like very easy. So linear interpolation for the xt and the difference between y and x for the ut.
It is shown in this theory section, right?
It is shown in the conditional flow matching model class. There are two functions, compute xt and compute ut.
I have a question. So with optimal transport, we assume that we have distribution between two samples.
Well, not exactly. So we solve the optimal transport problem on the distribution level. So basically we have two distributions in P0 and P1, two like overall, like not the particular time data points, but the whole distributions that we approximate by the mini batches, yeah. And then we take these mini batches that represent each of the distribution and pair those data samples in such a way that the trajectory between them, this linear interpolation, would be as short as possible.
So the value is not given between samples.
The value?
The probability, I mean.
You sample a mini batch and you say that all of the samples in mini batch are equally distributed.
And if I understood correctly, we can assume that they are not.
Not equally distributed?
Yeah.
Yeah, well, I think that as an extension you can make it work in the, if you will dig deeper in the POT library, then you can actually, assign some probability density to your samples and run optimal transport solver with these densities here.
But I have general question. What if we don't have probability but some normalized measure?
Oh, that's a very interesting question. Yeah, well, what do you mean exactly? So if you don't have samples, then, but you have some energy, a normalized density, or...
Yeah, for example.
That is very interesting question. There are actually, this is a different problem. So here we assume that we have data samples. However, there is a whole research field about when we don't have samples, but we do have a normalized density. And yes, there are approaches that train a flow matching model in this particular case. I do not remember like the name of the paper, but if you will come for me after the seminar, I will try to give you such names. But yeah, you can do this, but this is a rather more complicated procedure than this one.
Okay, thank you.
More questions? No questions. Thank you, Sergey.
Yeah, okay. So then I will continue with another transport couplings. So we have type independent coupling, this one, and optimal transport one, which is this one. However, let's ask the question, what is the worst possible coupling that we can have? And one can, for example, suggest that it would be an independent coupling because we have all the trajectories that do intersect and look like spider net. However, I think that the worst coupling should be this one. which is anti-optimal transport mini batch coupling. So in the previous version, we had tried to take the samples from our distributions, mini batches, and solve and try to find such couplings that provide less difference between the x and y's, or the less length to the our linear interpolations. However, here we also sample mini batches from both of these distributions and find the such couplings between samples x and y's that tries to maximize the length of linear interpolation. So this is the so these trajectories right here, linear interpolations, have the worst possible length, and this is like called as a anti-optimal mini batch, and it is don't ever use it on practice. This is not good, and this is in particular shown here to show you how bad can it be. And so again, we run the same optimization procedure. We also solve this optimal transport problem for each of the gradient step. However, we solve it in the negative, let's say, way. And again, it takes 1.5 minutes, which is 3 times, 3 times more time than for the independent one. And here is the result. Here is the trajectories. At first, they can seem like not very bad. Yes, they have some curvature, but it's but overall they are mostly linear and straight. However, you can see that I believe each one of these trajectories, they do have this one very sharp angle near the center. So let's follow some of the trajectories. For example, this one. I hope you can see. So it goes, it starts from this green sample, then goes to the center, then turns around, and then goes to the red sample. And that's what I believe every one of these trajectories does. Yeah, they first go to the center, and then they go backwards out of it. So to say the least, this is not very nice for the such OD trajectories are not very nice for the OD. It's not very nice for the ODE solver because right here, when this very sharp turn is happening, we can easily make an error for our ODE simulation. And I believe that's partly what is happening here, because you can see that previously these red samples, they have represented equally good round Gaussians. However, here in this particular case, we have this, for example, 3 Gaussians which are not very round, which are not very equal, and you can see that, for example, one of such Gaussians has less density than the other ones. That is partly because of, that is, I believe, mostly because of these bad trajectories. So yeah, that is the thing that you don't want to do. However, it still provides some way to train a valid flow matching model and still get some samples. And so we have seen the 3 possible ways to construct a flow matching model, and the next one is what the part of Alexander lecture was about, is the rectified flow, right? So if we want to straighten the trajectories of some flow matching model out, we can take already trained flow matching model and train another flow matching model on top of it, using the first flow matching model as a coupling, right? Because it starts from distribution P0 and ends at distribution P1. Then we can just take those samples as our pairs, and everything will be beautiful and fair and square. Yeah, so this is the thing that we will have here. However, there are some problems to this algorithm. First is that here we take the previously trained anti-mini batch model as a coupling for our, as a starting flow matching model for our rectified flow procedure. And you can see that anti-mini batch flow matching doesn't produce very nice samples. And unfortunately, with rectified flow, if we have some error in the procedure, it propagates further into the rectified flow model. So basically, if we have this like two Gaussians which are not very nice, we will further just multiply this problem and get more error. However, we will get straighter trajectories. That's true. Yeah, so let us implement the rectified flow coupling. So again, the only difference here is the way how do we do sample points x and y's for our regression problem. And here we implement the reflow sample function. So what is it doing? It constructs a sub data set from already trained flow matching model. So we have this already trained flow matching model, right? We sample points from our Gaussian in the middle from our source distribution, and then we generate the transport of it. The already trained flow matching model, which is this anti-mini batch flow matching model, and we construct a mini batch and we construct a data set out of them, and then we just in future we would use this data set for training of our flow matching model. However, it takes time. This is complicated in terms of computational resources procedure, and again, the inference of flow matching is not very fast, and yeah, we will spend a lot of time on it. So for example, for the preparing of such data set, we have spent 2 minutes, while the training of previous models took at most 1.5 minutes. So this reflow procedure already takes more time than like all of the previous flow matching models, even though we haven't trained anything yet. But yeah, so let's take a look at result wherever it is worth it. And again, we do the same training procedure, but the pairings come from our already trained flow matching model. And then we train the flow matching model, which just takes 30 seconds as an independent one because we do not solve any optimization problem in the beginning. And here's the result. So, well, these trajectories are actually quite straight. So you cannot, like, even compared to the optimal transport mini batch one, they are straighter because in the optimal transport mini batch one, we still had some curves here and there. But here, almost all the trajectories are straight. And well, that's great because we can do less steps with our OD solver during inference, and we will it will take for us less time. And also, you can see that previously, since I thought about this problem of error accumulation, we had this previous model as a start, and we can see that those two Gaussians, they were not represented very well. They were shallow, sparse, and it is logically to suppose that the rectified flow model based on this flow matching model as a coupling would also have problems with those two distributions. And we will have a lot of density in those two Gaussians at the corners. So let's see. And so you can see that the same error propagates into the next model. So those two Gaussians, which were bad in the previous anti-mini batch model, are also bad in this reflow model. And those two Gaussians at the corners that have had a lot of density still have a lot of density. So, but trajectories are straighter. So there are some trade-offs in the rectified flow model. But of course, in practice, you can do it a lot better and get the full, like, all nice 8 Gaussians. But and then we can compare all the 4 couplings, all 4 models. So first, we start from the independent one, which is one on the left, and we have curvy trajectories. Then we go to the mini batch optimal transport one, and we get significantly straighter trajectories on the right. Then we ask what is the worst possible case, which is anti-mini batch on the left, and we have very sharp edge for each of the trajectories, which is very bad and leads to bad samples. And then we have reflow that has straight trajectories. However, it induces the error from the anti-mini batch model that it was based on. So what is the conclusion here? What do you use in practice? Well, on practice, most of the models do use independent transport coupling. And yeah, well, though it seems like mini batch optimal transport coupling plan on the right can be very nice. However, it takes additional time, and in high dimensions, it doesn't really work well. So in practice, I believe most of the practitioners just stay on the independent one and then just apply reflow here on the right, but not based on the optimal transport plan, but based on independent plan. And that's basically, I think, how diffusion, this flow matching diffusion also works with ends-to-flow and our paper that Alexander told about. Yeah, so that is, I believe that's it for the first part, which took most of the seminar with respect to the different transport coupling plans. So if you have some quick questions, maybe it's time to get them, and then we will quickly go through the image generation with flow matching models.
I have a question about rectified flow. So in case of rectified flow, we use the trained model, right? And when we see the loss over time, it's really low. Can it be like the model is overtrained and it just remember everything, and because of that, its loss is really low?
Yeah, actually, well, that is very nice that you notice that loss is very low, because there are actually like theoretical justification for that. Because so we let's say that overall, the closer we are to optimal transport plan, the lower is the loss. So for instance, in the straighter the trajectories, the lower the loss. So that is like kind of the rule. And so this reflow with straight trajectories, we have very, very low loss. With optimal transport mini batch, we have like loss somewhere around 2. And you can see that for mini batch optimal transport plan, we also have loss which is 0.2, which is indeed higher than for the reflow, but lower for the anti-optimal mini batch, because the straightness of trajectories of this mini batch optimal transport plan is actually in between reflow and the optimal transport mini batch. So to answer your question, there is like some particular dependence on the straightness of trajectories and the resulting loss. I believe you can take a look into the conditional flow matching model for more detail, but that is a very nice question.
More questions? No questions.
Then let's go to the more or less scalable application of flow matching. So in most of the practical cases, flow matching is used for the generation of data in the high dimensional spaces. And for instance, images, which in our case would be MNIST dataset with colored images. So here's a little bit of a dataset setup. And by the way, so we use here a different library for the ODE solvers, which is called TorchGFEC, which is like analogy of TorchDin library that you can also find a lot of nice ODE solvers there. So you can try both TorchDin and TorchDFAC. Yeah, so here's the class of the colored MNIST dataset. We just take the images from MNIST dataset and color them into 6 colors. So yeah, as you can see, some of his samples, yeah. So in our particular case, we take not all the MNIST samples, but only digits of 3, and color them into 6 colors, which, well, there's also yellow here, but yeah, so green, purple, red, bluish green, red, purple, and there should be also yellow. And that is our target distribution. And our source distribution, again, is just a Gaussian. And the Gaussians for the, we just take the image space and induce a Gaussian upon it, and it looks like this. Again, just, random pixels, basically. And our task is to take samples like on the top and transport them into the samples on the bottom here. And again, we train a flow matching model for it. What is, well, there are not a lot of different things here from the previous one, maybe except for the neural network, which here in this particular case is more complicated one. It is a conditional UNet imported from diffusers library, which has a lot of nice models that you can utilize for the diffusion models, for the flow matching models, for the beach matching models, which will be shown tomorrow. And it has proper conditioning for the time input. So we define our UNet model. Again, define the forward function, which is just the forward of our vector field. Utilize show the linear interpolation, just like in the previous case. Then compute the target, just as in the previous case, and make a sampling procedure, again, just as in the previous case. However, we use different library here, so it's a little bit different. But overall, yeah, they are like TorchDiff and TorchDin library are, I believe, mostly equivalent. And the training loop is very, very similar, just with addition of learning rate scheduler. Again, we train our model for several epochs. And here we utilize the independent transport coupling plan. So we just sample from a Gaussian, we sample the MNIST images, we pair them absolutely randomly, and construct our optimization problem that we solve, and everything is great. Again, loss is just mean squared error. Yeah, very simple and easy. Hyperparameters still are, there is no place to make a mistake. And then we can train a flow matching model. It takes 10 minutes on the GPU A100. And here you can take a look at the samples. So yeah, you can actually see that model did quite well. So it actually outputs, this is already a result of inference. It outputs quite decent digits of 3 that are colored in different ways. So I think that you can see here all these 6 colors: green, yellow, purple, red, blue, and something bluish. Yeah, this is actually like quite nice generations, which are, as you can see here, quite similar to the target image that we want to generate. And again, we just start from this random pixel noise, apply our flow matching model with ODE simulation, and get such samples. And that's it. So this is quite short demonstration on the image task. And I think, so that's mostly it. So what have we learned here? We learned here the implementation of the flow matching model, that it is very simple. You have to just implement several functions and get the right neural network. And if you want to get your trajectory straighter, then you can go either for mini batch optimal transport coupling or do a reflow procedure. And you can apply your flow matching models for the higher scalable applications such as image generation, even for text to image generation and etc. And it will do just fine. Yeah, so I think on this note, that's it. So again, if you have some questions, I'm happy to answer them. Yep. If you have some additional questions, you can ask me in the middle. But yeah, so thanks.